Fighting Falcon just reached a whole new level. This iconic multirole fighter, trusted by over 25 countries for its exceptional maneuverability, long combat range, and all-weather targeting, now boasts a cutting-edge engine upgrade. With increased thrust and efficiency, this powerful addition promises to enhance its speed, agility, and operational reach. How will this advancement redefine air combat capabilities? What tactical advantages will it bring to the battlefield? Join us as we unveil the capabilities of the powerful F-110 engine that just transformed the already formidable F-16 into a global threat. The F-16 has always been a force to be reckoned with. Created to dominate the skies during the day, this aircraft was later improved to handle many different missions in all kinds of weather. Since its first production in 1976, more than 4,600 of these versatile planes have been made, showing their continued success and importance in modern air combat. Its ability to adapt to changing needs has made it a reliable choice for various roles, from air defense to ground attacks, solidifying its place as one of the most widely used aircraft in the world. The F-16 may be smaller and lighter than earlier fighter jets, but it is packed with advanced technology that makes it incredibly agile and powerful. One of its most impressive features is its use of advanced aerodynamics and avionics, including a unique flight control system called Relaxed Static Stability/Fly-by-Wire, which improves its maneuverability. The F-16 was the first fighter designed to handle extreme 9G maneuvers, and it can reach speeds faster than Mach 2. This jet is full of innovations designed to improve the pilot's experience and performance. The frameless bubble canopy offers better visibility, while the side-mounted control stick makes it easier to handle. The pilot seat is also reclined, reducing the effects of G-forces during sharp turns. For weaponry, the F-16 has an internal 20mm M61 Vulcan cannon and can carry a range of missiles, bombs, and pods. With a thrust-to-weight ratio greater than 1, it has the power to climb rapidly and accelerate vertically. Designed to be more cost-effective and easier to maintain than older jets, the F-16's airframe is made from 80% aviation-grade aluminum alloys, 8% steel, 3% composites, and 1.5% titanium. The design includes advanced features like bonded aluminum honeycomb structures and graphite epoxy coatings for the flaps and fins. The aircraft has fewer lubrication points and fuel line connections, which makes maintenance quicker and simpler. Around 80% of the access panels can be reached without the need for special stands. The air intake is positioned to reduce drag and ensure the jet performs efficiently. Initially, the F-16 was designed for a 4,000 flight-hour lifespan, with the ability to handle 7.33 G maneuvers. However, engineers went above and beyond, designing the airframe to last for 8,000 hours and handle 9G maneuvers with full fuel. This extra durability proved beneficial as the F-16's role expanded from air-to-air combat to a versatile multi-role aircraft. As the mission requirements evolved, the F-16 gained additional systems, which added weight, prompting several strengthening programs to ensure it could handle the extra load. If this aircraft was initially termed formidable, its new engine, the F-110, has transformed it from a respected aircraft to a global threat. How exactly did this engine transform this respected United States multi-role fighter? Let's check out what exactly makes this engine revolutionary. The General Electric 110 is a powerful jet engine designed to boost fighter aircraft performance. It was built by GE Aerospace, uses an afterburning turbofan system, and was created as an alternative to the Pratt & Whitney F-100. The F-110 was originally developed from the F-101 engine and first used in the F-16C Fighting Falcon and F-14A+ and B Tomcat. Over time, it was also chosen to power newer versions of the F-15 Eagle. This engine is manufactured not only in the United States, but also internationally through licensing agreements. IHI Corporation in Japan, TUSA's Engine Industries in Turkey, and Samsung Techwin in South Korea all produced the F-110. During the 1970s, General Electric aimed to re-enter the U.S. fighter engine market while the Air Force searched for solutions to the reliability and maintenance problems of its Pratt & Whitney F-100 engines used in F-15s and F-16s. GE began developing the F-101X, an improved version of the F-101 engine, originally designed for the B-1 bomber. This new design featured a smaller fan borrowed from the F-404 engine, making it more suitable for fighter jets. The iris nozzle, also from the F-404, was adapted for this engine. When the Carter administration canceled as the B-1A bomber, GE shifted its focus, hoping to offer the F-101X to the fighter market. The Air Force showed interest and started funding the project, renaming it the F-101 Derivative Fighter Engine. This competition was part of a broader effort to push Pratt & Whitney to improve the F-100. In 1980, the F-101 DFE completed ground tests and was fitted on an F-16 for flight testing, demonstrating significant performance gains. By 1982, the Air Force committed to full-scale development, eventually naming it the F-110 GE-100. This sparked the so-called Great Engine War in 1983, a fierce competition between the F-100 and F-110 engines. Contracts were awarded annually based on performance and cost, resulting in both engines being used by the Air Force until the competition ended in 1992. The F-101 DFE also showed its potential on the Navy's F-14B prototype in 1981, outperforming the TF-30 engine. While initial testing was paused, the Navy later adopted the engine, designating it as the F-110 GE-400 for future F-14s. GE's persistence and innovation allowed the F-110 to become a key player in military aviation. In the mid-1980s, the U.S. Air Force wanted more powerful engines for its tactical fighters, leading to the Improved Performance Engine program. This resulted in the F-110 GE-129, which increased thrust to 29,900 pounds in the afterburner. It introduced new technologies like a digital engine control system, allowing higher thrust in more conditions. It debuted in 1992 with the F-16 C and D Block 50 and later upgraded F-15E variants, starting with the F-15K in South Korea. The F-16 Fighting Falcon originally entered service with the Pratt & Whitney F-100 afterburning turbofan engine. However, to reduce costs and improve efficiency, the United States Air Force launched the Alternate Fighter Engine program in 1984. This initiative allowed engine manufacturers to compete for contracts, leading to the adoption of the General Electric F-110 engine. By June 2005, an impressive 86% of the USAF's F-16 CD fleet was powered by F-110 engines. The F-110 GE-100 offered about 4,000 pounds more thrust than the F-100 PW-200, but it required additional airflow to perform at its peak. The standard inlet design, known as the normal shock inlet, restricted the F-110 thrust to 25,000 pounds. To solve this, engineers introduced a larger inlet design called the Modular Common Inlet Duct, also nicknamed Big Mouth. The F-16 C and D Block 30 and Block 32 were the first variants to feature a common engine bay, allowing them to accommodate both the F-100 and F-110 engines. The Block 30 models were equipped with the larger MCID inlet for the F-110, while Block 32 retained the standard NSI inlet for the F-100. The F-16 C and D Block 30 and 40 aircraft used the F-110 GE-100 engine, producing 28,000 pounds of thrust. Later, the Block 50 variant introduced the F-110 GE-120-9 improved performance engine, boosting thrust to 29,500 pounds. For the advanced F-16E and F Block 60 used by the United Arab Emirates, the F-110 GE-132 was developed, delivering an even more impressive 32,500 pounds of thrust. This engine was also proposed for the Lockheed Martin Tata F-21, a Block 60-based model aimed at the Indian Air Force's Marka competition. The latest production model, the F-16C Block 70, features the F-110-129D engine, which is designed for greater durability and a longer lifespan. Two F-16 derivatives, the Mitsubishi F-2 and the General Dynamics F-16 XL, also use the F-110-129 IPE engine. For the F-2, the engines were built under license by Japan's IHI Corporation, where they were designated as the F-110 IHI-129. However, in 2024, IHI Corporation faced scrutiny after a whistleblower revealed that its subsidiary, IHI Power Systems Company, had been falsifying engine data since 2003. This scandal affected over 4,000 engines worldwide. Japan's Ministry of Land, Infrastructure, Transport and Tourism launched an investigation into the matter in April 2024, casting a shadow on IHI's reputation. Despite this, the F-110 remains a cornerstone of the F-16 program, showcasing its adaptability and performance in various configurations across decades. Now, as the iconic F-16 Fighting Falcon celebrates 50 years of service, it's a perfect time to look ahead and explore how this legendary fighter will continue to meet modern and future challenges. While the U.S. Air Force is gradually retiring older F-16 models, the newer Block 40 and Block 50 variants are set to remain in action well into the 2040s. To stay relevant, these aircraft will undergo significant upgrades to enhance their performance and combat capabilities, even more upgrades than equipping it with a Fearsome engine. To this effect, a total of 608 Block 40 and Block 50 F-16s, often referred to as post-block aircraft, will receive these critical upgrades as part of the Post-Block Integration Team initiative. This ambitious program, led by the Air Force Lifecycle Management Center's Fighters and Advanced Aircraft Directorate, involves up to 22 advanced modifications designed to boost the F-16's lethality and adaptability. These upgrades aim to ensure the fourth-generation fighter stays effective against evolving threats in a rapidly changing battlefield. From modernizing avionics and radar systems to enhancing weapon capabilities and survivability, the POBIT project reflects the Air Force's commitment to keeping the F-16 relevant and combat-ready for decades to come. This effort ensures that the F-16's remarkable legacy will continue to soar, even in the face of future challenges. Former Air Force Chief of Staff General C.Q. Brown, Jr. expressed optimism about the ongoing upgrades to the F-16. He highlighted that these improvements would enhance the aircraft's combat effectiveness and adaptability in an ever-evolving electronic warfare environment. Brown emphasized the importance of modernizing the F-16 to maintain air superiority in the future. The Post-Block Integration Team Upgrade Program, which was launched in 2022, is being implemented alongside the Service Life Extension Program, or SLEP. The SLEP focuses on extending the aircraft's operational life from 8,000 to 12,000 flight hours. This involves extensive structural modifications, including replacing bulkheads and longerons, strengthening wing assemblies, adding new brackets and beams, and reskinning the upper fuselage. Each aircraft undergoes a detailed 9-month refurbishment process at multiple locations across the United States and Europe. A major component of the POBIT upgrades is the integration of advanced technology. The APG-83 Scalable Agile Beam Radar, equipped with active electronically scanned array, is a key feature of the program. Alongside the center display unit, the new radar system provides pilots with enhanced situational awareness. It allows for synthetic aperture radar mapping, enabling the detection and engagement of both air-to-air and air-to-ground threats at significantly longer ranges. These upgrades are expected to transform the F-16 into a more capable and resilient aircraft. By combining structural improvements with cutting-edge technology, the program aims to ensure that the F-16 remains an essential asset for modern combat operations well into the future. The F-16 is also getting new improvements like the Link 16 for better data sharing, updating the cockpit and mission computer, and switching to a high-speed data network. The upgrades also bring next-generation electronic warfare systems, a communication suite upgrade, and a programmable data generator, along with several other advanced hardware changes. These updates are being introduced in phases to keep the F-16s operational while modernizing the fleet. The oldest F-16s in the post-block fleet are the Block 40 and 42 models, which started production in late 1988. The newest is a Block 50, delivered in March 2005. Before the POBIT program, the biggest upgrade was the Common Configuration Implementation Program, which ran from 2000 to 2010. This effort brought 651 Block 40, 42, 50, and 52 variants to a common standard with major improvements, such as new mission computers, updated cockpit displays, and improved data links. Later, the focus shifted to adding an advanced AESA radar, which had been long overdue. Early attempts didn't succeed, but a new opportunity came when the U.S. Northern Command identified an urgent need for a radar upgrade for pre-block F-16s used by the Air National Guard for Homeland Defense. The Air Force chose the Northrop Grumman AN/APG-83 S-Sabre radar for this mission. After its success with the Air National Guard, the same radar was selected for active-duty F-16s, ensuring that all operational F-16s benefit from this powerful technology. The F-16 is also receiving a variety of advanced upgrades to enhance its combat capabilities, starting with the powerful new radar system from Northrop Grumman. This radar is designed to fit the F-16 without needing any structural changes, power adjustments, or cooling upgrades. It enables the F-16 to detect, track, and identify more than 20 targets at once, faster and at greater distances. Additionally, the radar includes synthetic aperture radar mapping, which provides high-resolution images in all weather conditions. The system also has strong electronic protection, allowing it to operate effectively in challenging electronic warfare environments. Another key upgrade is the addition of the center display unit, first installed in Air National Guard jets in 2010. The CDU replaces the old instruments on the center pedestal with a high-resolution, multi-function color display. This upgrade helps pilots take full advantage of the new radar and improve targeting pods, while also reducing their workload and enhancing safety and efficiency during missions. As part of the post-block integration team program, the F-16 is also receiving the Northrop Grumman N/ALQ-257 Integrated Viper Electronic Warfare Suite. This next-generation system replaces older electronic warfare equipment and is fully integrated with the new APG-83 radar. The IVOS is designed to meet the requirements of open mission systems and offers long-term growth potential to accommodate future upgrades, such as the fiber optic tow decoy and adaptive processing. The suite also includes a radar warning receiver, though some details are still unclear due to an ongoing contract with Raytheon for additional radar warning receivers. One major benefit of the IVEWs is that it is completely internal to the aircraft, removing the need for external electronic countermeasure pods like the ALQ-131 and ALQ-184. This allows the F-16 to use the centerline station for external fuel tanks or other payloads, maximizing its versatility. The IVWs can also jam current and future threats, greatly enhancing the aircraft's ability to defend itself in hostile environments. Alongside these upgrades, the F-16 is receiving improvements in countermeasures as well. The weapon pylons on stations 3 and 7 have been equipped with Terma's Pylon Integrated Dispenser System, which improves the capacity for chaff and flare countermeasures. Additionally, a contract signed in 2020 will deliver the new Pylon Integrated Dispensing System Universal, featuring 3 chaff flare dispenser magazines and provisions for future missile warning systems. The Air National Guard is also introducing new systems, such as the ASQ-236 Dragon's Eye AESA radar pod, which offers detailed surveillance maps and coordinates for bomb impact assessments. This system complements the APG-83 radar, making the F-16 even more capable in combat. Another exciting development is the fielding recommendation for Leonardo's Bright Cloud 218 expendable active decoy. The Bright Cloud is a self-contained, battery-powered decoy that can be dropped from the aircraft to confuse incoming missiles. It creates a significant distance between the aircraft and the decoy, allowing the missile to miss the aircraft entirely. These upgrades are just part of the many improvements the F-16 is receiving, with more developments expected as technology continues to evolve. The F-16's enhancements ensure that it remains a formidable force in modern air combat, adapting to new challenges and maintaining its effectiveness for years to come. To keep the aircraft in peak condition, every time an F-16 reaches 400 flight hours, it undergoes a major inspection in the phase dock. During this process, 136 panels are removed to thoroughly check the areas beneath them. Along with the 400-hour inspection, other checks are conducted to ensure the aircraft is fully operational. The inspection process is a team effort, involving F-16 crew chiefs and specialists from various fields like weapons, avionics, and fuel shops. Through careful coordination, the aircraft is made ready to return to service, fit to fly and perform its mission effectively. The goal of this phase is to ensure that the pilots get 400 more safe flight hours before the aircraft comes back for another inspection. Just like any vehicle, the F-16 Fighting Falcon needs regular maintenance and repairs. Most of the maintenance can be done with the engine still in the jet, but for some major fixes, the entire engine has to be removed. For instance, when we discover a damaged hydraulic line, it is not possible to repair it with the engine in place, so it's necessary to remove the engine to replace the line. Before the engine can be removed, the jet must be disarmed, and the weapons must be carefully taken off the F-16 wings to ensure safety. Once the weapons are removed, the process of detaching the engine from the airframe can begin. It takes over an hour to separate the engine and then carefully pull it out of the aircraft. The engine is heavy, and as it comes out, it can cause the aircraft to shift. The crew have to be careful and make sure the aircraft stays level as the engine is pulled out, so it doesn't put extra strain on the airframe. With the engine safely removed, the hydraulic line is replaced, and then the maintenance team continues with repairs on the rest of the F-16s. Each task is important, and working as a team ensures that the jets are always ready to return to action. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.